Thanks very much. As they said, I'm Jan. I work at ASI Data Science, and we are a data science consultancy. We do data science training, and we build a data science platform. And I work on the consulting team mostly, and a little bit on the platform. And today, I want to talk about how humans can support algorithms and vice versa with the interactive Python ecosystem. So I'm going to start by doing some fairly basic and fairly crude, because they're taken from Wikipedia, overviews of machine learning. Most people who sort of start out learning machine learning learn about supervised learning, which is learning a function that maps an input to an output based on example input-output pairs. And in particular, we often call this labeled data, right? So you have a big set of labeled data. You want to train some sort of algorithm, some model, in order to be able to predict maybe unseen input data, and basically learn the sort of input to label mapping. And then the other sort of side of the coin is unsupervised machine learning, where we usually don't have labels. So we have unlabeled data, and instead what we want to do is sort of understand the structure of the data. So often this involves clustering and various approaches like that. And they help you sort of figure out what's inside your data, maybe identify sort of groups of points that are defined by being sort of near to each other in feature space, and that maybe all have the same label, if you were to have labels. And so obviously, supervised learning is pretty advanced these days, so there's great libraries in order to do it. It's pretty straightforward, and if you have a lot of data, and it's good data, you can achieve pretty high accuracies at predicting labels. Unsupervised learning is getting there. You can do really amazing stuff with unsupervised learning algorithms. But ultimately, if what you want to do is predict some labels, and maybe you know which labels you predict, you just don't have any examples of it in your data, you're going to struggle a little bit. And so ideally, what you want to do is you have unlabeled data, and you may be doing some unsupervised learning, and you want to start moving towards using supervised machine learning algorithms in order to start predicting your data. And there's sort of something in the middle which not that many people learn about when they start out doing sort of ML courses, which is semi-supervised learning, where you have some labeled data, but you also have a lot of unlabeled data. And you want to start training algorithms that take into account both. And so usually that means that you sort of make some assumptions about your data, about the labels and the unlabeled data, maybe that they all lie on some sort of continuous manifold, or that there is some sort of clustering inside your data, and you try and extend the sort of labels that you do have towards the data that you don't have labels for, and try and improve your algorithm that way. And so that is the main thing I want to talk about today, and in particular a sort of subset of this, which really comes back to the sort of moving from unsupervised learning to supervised learning, and that is active learning, which is the case where you have some supervised machine learning algorithm, and the algorithm is able to interactively query some information source, and that's usually a user or a data scientist, and is able to basically obtain new labels. So it's able to ask, OK, I'm starting to make some predictions, but I'd like to improve. Can you tell me the label for this particular data point? And then hopefully it will sort of improve iteratively like that. And so I've got some diagrams to illustrate this using a fairly simple case. So if you have some 2D data that's mostly unlabeled, so those are the gray points, but you have two labels, the red and the green, and you train some sort of linear model, you might get a model that has a sort of function that looks like the red dashed lines here. So you have some sort of decision boundary in the middle, plus some uncertainty area, because maybe you're using a parametric model where you can estimate the sort of variance of your model parameters. And now we want to know, A, how good is this, and B, how can we improve this? And what we could do is just start labeling more points, right? We could just look at some of these points, and the user could look at it, say these are images. The user could look at it and say, OK, that is a horse, which is fine, but what we want to do is do this in a sort of relatively smart way, and we can because we have some information about a model at this stage, right? We know the decision function of this model. And so what we might want to do is not just query a random point, but query a point that is fairly close to the decision boundary and where the model is relatively uncertain compared to some of the other points in the feature space. And so then we label that point, and it's a red point, and so our decision function shifts to this. And now we can label some more points, because now we have a new model, we have a new decision function, and we have a different relationship between the points and that decision function, right? So we could now start to, if we were to want to sort of efficiently label this, we could maybe label this point because it's fairly close to the decision boundary. And if that's a green point, then we're starting to really shift our decision function. The uncertainty area shrinks by quite a lot, and we're really getting somewhere with this model and our predictions on the unseen, on the unlabeled data. So that's a fairly sort of simplistic example using low-dimensional data and a fairly straightforward model. But the sort of basics of the active learning process are pretty much there, right? So it's these 5 steps where you train some supervised model on labeled data. You then use that model to make predictions on unlabeled data, and then you somehow use the information that your model is giving you to prioritize the unlabeled data. And then you use that prioritization to label more data. And then you rinse and repeat until you have labeled quite a lot of data and maybe are achieving some performance that you're satisfied with. I want to mainly talk about the yellow parts, just because training a supervised model is a whole other talk's worth of information, and making predictions, especially using sort of supervised learning libraries, is pretty good, pretty easy these days in Python. And just to sort of come back to why using this approach is really nice, is that we use exactly the same models that we use in standard sort of supervised machine learning to do this process. We don't have to really change very much. We can probably use the same Python libraries for it. And hopefully we don't need to sort of learn anything new about algorithms that we're not familiar with. OK. And so to talk about these various steps, I'm going to illustrate it with a library that I've written for this purpose, which is called Superintendent, and which heavily sort of leverages the interactive Python ecosystem, because ultimately you don't want to spend ages building some sort of labeling app where people can click on buttons and stuff. Instead, what you want to do is use the existing sort of infrastructure that Python already provides, and in particular Jupyter and the sort of IPython ecosystem, to do this fairly seamlessly and painlessly. And that's what I'm trying to create. OK, so we're just going to start with the first step, which is we want to train a supervised model on some labeled data. So that means if we don't have any labels at the beginning, we need to create some labels. And I'm just going to demonstrate that. This is our data science platform, but ultimately this is just a Jupyter notebook, as you will see. And I'm going to demonstrate this stuff with, the classic, the MNIST digit dataset, that I'm just importing from sklearn here, where we've got some images that we want to classify as to whether they're the digits from 0 to 9. And obviously, we have labels for this, but let's pretend that we don't. So what we want to start doing is create some initial labels. I've just selected 1,000 of these images. They all look roughly like this, so they're fairly low resolution. But we want to start labeling these. And so what I'm going to do is the class that you need for this from the superintendent package. And then I will create a data labeling widget. And I'm going to use, because these are images, I'm going to use a factory function that creates it sort of to display images, because obviously images isn't the only thing that you want to label these days. And I'm going to pass it the features that I created earlier. So hopefully that will work. And then I can start to label it. And I happen to know that this data set has the digits from 0 to 9 in it, so I'm going to specify that the options that I want to be labeling with are from 0 to 9. Oops. And so then we've kind of got, based on the sort of IPyWidgets framework, a sort of labeling object that we could start to use to label. And so I can start clicking on these buttons and create labels for my data. And you're not seeing it because I'm doing it very slowly, but you're getting a little progress bar up here as well, so you always know how much you've got left to do. And you can then, because this is just a Python object, access these labels immediately. So most of these are none because I haven't done that much work. But you can see that my labels are in here. And so if I wanted to, I could now start training a model, right? And I don't have much data, but I could. Cool. So that is the first step. So we have achieved some labeled data. And now what we want to do is we want to use the labels that we have created to prioritize the labels that we still need to create. So that's step 3. And I'm just going to quickly talk about sort of how you might do that, because for the simple case of the linear model that I had earlier, it's maybe pretty straightforward, but with a more complex model where you don't have access to the actual decision function, it's not so easy to say, okay, this point is right on the decision boundary. But what most active learning algorithms rely on is the simple fact that you get continuous model output from quite a lot of different machine learning algorithms. And so this is where you can test your own handwritten digit recognition algorithms using my diagrams here. But if you have, the 2 images on the left, so there's 4 and there's 8, and you're passing it through some model, then you're getting some continuous output from that. And that might be the probabilities of the different labels, if you've got a model that produces that, but it could also just be, the softmax output layer from a neural network or something like that. As long as it's continuous and as long as the actual values of this output correspond in some way to the sort of certainty that you have about the label. And so, for example, if this algorithm has seen quite a lot of 4s, then for the first image, it might produce probabilities like the ones on the top, where everything is fairly low, but the probability of it being a 4 is quite high. And so, we're fairly certain that, that this is a 4. Whereas the image on the bottom, because it's a fairly badly written 8, maybe the probability of 8 is quite high, but actually the probability of 0 is a little bit higher. So that's the one that wins out here. So how do we then use this continuous model output to prioritize the data? So I'm going to talk about 2 simple ways of doing that. The first one is to sample your unlabeled data using the sort of entropy of these predictions. And so you just compute the entropy across the different probabilities of the labels. In this case, the top prediction is fairly certain, so the entropy is quite low because most of the information is in one label. Whereas the entropy for the bottom continuous model output is quite high, so we prioritize that point over the top point. And note that this is kind of regardless of whether we know whether that the label that the model is producing for 8 here is correct or not, right? We're not actually evaluating the accuracy of the model here. We're just saying, okay, we happen to know that this model is fairly certain about the top image, but not very certain about the bottom image. So that's nice. That would be one way of doing it. And another fairly simple way is to simply compute the margin in between the top probability and the second highest probability. So in this case, the model is 91% has a 91% probability of the label 4, and the next highest probability is 1%, so the margin is 0.9, whereas for the bottom image, the margin is 0.02. We take the image that has the smallest margin and start to label those images. So this is another way of kind of quantifying the sort of certainty of the model about the various images, and therefore prioritizing which images we need to sample first, we need to label first. And just to sort of illustrate that this can be quite powerful, this is from a paper about active learning where they're comparing different active learning sort of prioritization mechanisms with just selecting at random, which is on the red line here. And as you can see, the BVSB, which is actually the margin sampling I just spoke about, performs quite a lot better than the random sampling, and you achieve much higher performance much quicker. Cool. So how do we do that in Python? Well, first we maybe need to collapse some of these cells. And so what we want to do is we want to first choose an algorithm that we're using here, right? Because that's, in order to get this continuous model output, you need some model. And so I'm just going to import a very simple one, which is a logistic regression, which isn't exactly state-of-the-art for MNIST digits, but it achieves about 94% accuracy. And I'm just going to use the default parameters for this model as well. So I've created a model which sort of conforms to the standard sklearn, fit, predict interface. And then I can just pass that to my labeling widget as a classifier. I need to specify how this widget is going to reorder the data anytime I ask it to. And then I also need to specify how much of this sort of reordering is supposed to be done at random. In this case, I'm just going to choose 0 because it makes the demonstration a bit easier. And then I can start labeling. So I obviously start out with 0 labeled data, but I can start labeling in exactly the same way as I did before. So I'm going to skip. And create some labels that we use to sort of seed the algorithm that we're training here. Some of these are really hard. And once I've created some of these labels, I can hit this retrain button, and that's going to retrain the model. And at the same time, reorder all the subsequent images that I'm going to label based on the metric that I specified here, which is this margin sampling of the top 2 probabilities of the model output. And so what we'll see is that we're sort of starting to explore fairly similar areas of the feature space, right? This 0 is fairly similar to the 6, and presumably that's why the sort of margin between the top 2 probabilities is fairly low. And then we've got 2 5s, so the model is clearly not yet certain about 5s, and we're starting to sort of explore the feature space where it maybe is most useful to the model. And we can then keep doing that and keep retraining the data and hopefully start to sort of teach the model a lot more about the areas of the feature space that it doesn't yet know about. Note that the score here is still fairly bad. I haven't labeled very many images, and in particular, I'm mainly labeling the really hard images, right? And this is where this sort of shuffle proportion comes in, because in order to assess your model performance, which is this value here, you really want to have a fairly representative sample of your feature space, which I'm not doing here. So you want to have some randomly sampled images in order to be able to produce your sort of model score. Cool. So that's how you might want, how you might sort of do this active learning using this library. And this is the next step. This is what I just did. You then, once you prioritize your data, you want to label more and more of it, right? So you want to keep going. This I've just done. And then ultimately, what you want to do is repeat this lots and lots of times, right? Especially if you have a big data set where maybe you're not quite certain that sampling a small proportion of it will sort of hit all the different areas and maybe find all the sort of minority classes in your data set. And that can be quite boring, as you just saw. Sorry about that. And so what I am trying to, what I've built into this library is the ability to sort of distribute this across a few different people. And so ideally what you want to do is you want to collect all the labels that people are creating and train an algorithm based on that, based on all of the data that different people are providing, then reorder it, and then have everybody who's doing the labeling take the next sort of images or next data that they're labeling from that sort of same stack of data that, that you're kind of labeling. And so in order to do that, you can connect this library to a database where essentially you can have the two people at the top create a widget to take sort of images off this queue, which sits in the database, and just keep labeling, and they don't even know about the algorithm that you're using to reorder this. And then you can have the person at the bottom, or the server at the bottom, run this orchestration function, which keeps retraining the model periodically and keeps reordering the data based on whatever method of sort of reordering you've chosen. And I'm just going to demonstrate that as well. So what I'm going to do is I'm going to spin up a completely different server, which is going to do this stuff for me. And all you need to do on that server is run a script that looks like this, where effectively you're doing a lot of the stuff that we just did in the notebook. You sort of import a model, and then in particular you need a sort of database connection, which just follows the sort of SQL Alchemy database connection string format. And then you provide that to your Python object here, and in particular you import the widget from a subpackage called distributed, and then you just run this orchestration function. And by default it will sort of retrain the model every 30 seconds, and then reorder the data. And obviously that means that you can have the server that is sort of doing this orchestration be much more powerful than the labeling servers or the people's individual laptops or whatever you're using to actually run the labeling. And I'm just going to run this, and then anybody can, in their Jupyter notebook, do exactly the same, load the same sort of database connection in. So again, it looks a bit like this, and start labeling. And because I've practiced this talk, you can see that there's actually a bit of progress here already, and I can start sort of labeling the data. And if I had people working with me on this, they might be doing the same thing by themselves. But we're all sort of labeling from the same queue. And I'm just going to provide the different options here. Cool. So, in theory, that means you can have lots and lots of people doing this. We've done this with about 20 people at the same time. It's been quite useful for us building a sort of face recognition algorithm, and it does speed up labeling by quite a lot. Cool. And so just to finish that up, I've got a few different things planned for this package. Adding additional front-end options, because you might not want to have to require people to actually run a Jupyter server by themselves, adding sort of different queuing systems, and adding specific use cases. So I've been using this sort of image factory method to create these widgets. Doing something more specific for NLP would be nice, and implementing different active learning algorithms would be nice as well. So if anybody's sort of interested in that sort of stuff and has experience with it, then let me know, and please contribute. And also please use it. Cool, thanks very much. So what questions do you have?
Questions? One over there. Yeah, it's you.
Is there a microphone?
In front of you.
What, every seat
Okay,
has
hi.
Every two.
Okay, great. Two quick questions. So first of all, to the extent you're focused on retraining labels based on this cross-entropy concept, how are you ultimately judging accuracy? Is the assumption you still have some sort of label test set holdout, and that's what you're measuring the ultimate model against?
Well, you start out with, at least in the sort of fairly simple case, you start out with absolutely no labels, right? So it's quite hard to sort of think about the concept of a holdout set. The way this sort of score up here is calculated is using a sort of threefold cross-validation. So it's actually evaluating on the data that you've labeled, because in theory, that's the only labels that you have. So this is why, labeling the sort of edge cases, as I was doing here, doesn't lead to a particularly big improvement on those edge cases itself, because those are the hard images, right? But if you want to have that sort of, this metric be a bit more representative of your whole data set, you could sort of increase the random proportion of images that you're labeling and sort of try and get a fairly representative sample of your feature space.
And that was going to be my other question. Do you have any sort of anecdotal comments on, in terms of sorting the highest entropy observations to relabel,
yeah.
what % of the total training set on every batch do you need to focus on to start to get accelerated accuracy improvement?
So usually, if your model doesn't, if the sort of forward pass through your model doesn't take too long, then ideally you actually evaluate the entropy of your predictions on every single unlabeled data point, which ideally gives you the sort of best chance of catching the sort of edge cases that will improve your model. I mean, with the sort of image recognition stuff, people usually do this in sort of batches of 50, and they look at the entire data set when they're sort of reordering it. Yeah.
As well as active learning, have you ever tried this on active deployment? So putting this into a multivariate, landing page, for example, landing page optimization, whether you could not just learn actively, but actually deploy actively, so it improves the output as it goes through, whilst retraining itself at the same time.
Yeah, sorry. So the question is whether you can actually sort of put this into deployment and use it to sort of continuously update whatever you're trying to deploy. I suppose, yes. I don't run any landing pages, so I haven't done that particular use case. Mainly, we use this when sort of building models that we then later deploy. So I haven't deployed any of this live.
Have you tried to use it like in a transfer learning approach when you have like pre-trained model on some like ImageNet or something, and then you have your own data that you want to make this model perfect, yeah? So,
Mm-hmm.
so you do not train from scratch, but you actually update the existing model. Is it possible, and have you tried it?
Yes, so that's definitely possible, because ultimately what you're doing here is you're just providing any model, whether that is pre-trained or whether that is sort of completely fresh. The main worry with that would be that you're kind of making predictions. Now you'll see my screensaver. That you're making predictions on data using a pre-trained model and then reordering the data based on those predictions, right? So the problem there is that the model might start out being completely certain about specific points in the feature space, but it might be completely wrong. So yeah.
Would it be easy to integrate with like Amazon Turk type of services? Have you thought about that?
I think so. Again, something I haven't actually done, but that is what this was sort of initially designed to be. So we're currently experimenting with a different front end for this, which is using Plotly Dash, which actually produces, a website, so people don't need to actually deploy anything on their own machines, and that works pretty well. Yeah.
I was wondering if it's actually so you get this sort of major optimization thing that gives you the most the examples to label with the most information tables, for example. I wonder if that's actually, if you're using actual people to label the data, if that's the optimal thing to do. I wonder if you choose examples that are right on the decision how to rely on the model, it's going to be quite hard for a human to also label them. If they make a mistake, that might skew the training process quite severe.
Yeah, absolutely. That is definitely a limitation of this process in general, using humans to label the data. I don't think that's particularly exacerbated by this. The main thing that you need to sort of make sure is that you have this skip option, so people actually don't label something when they're not very sure about it. yeah, so that's definitely something that you need to be careful about. And in particular, we have this other option by default. So, when we were labeling faces, for example, building a sort of face recognition thing, you need to be able to just say, okay, this is a person that we haven't seen before, so let's ignore this or create a new label for it. Yeah.
Time for one last question, yeah?
Could you use the microphone, please?
Hey, have you encountered this problem that the active sampling of items gives you items that are very similar to each other? Because I actually implemented this sampling strategy, and that was the problem that I had. And also in this case, the retraining step took basically overnight, so I couldn't really do it as often. So
yeah, definitely. So usually, if the model is uncertain about a particular area and feature space, and you have a lot of data in that area of the feature space, then yes, those will be the ones that sort of get shown initially. And then if you're not retraining very often, then you're kind of oversampling that part of the feature space. That's partly why I've implemented this sort of shuffle proportion here. Because you want to still be able to randomly sample in addition to using the sort of active labeling, just because otherwise you might end up completely, undersampling the areas or sort of the images that you have lots of and that you want to be really sure about. Yeah, the sort of retraining thing in particular. Obviously, when you're building bigger algorithms, you want a lot more compute, and so that's why this sort of orchestration thing, where the computing happens on a different machine to the labeling, is quite nice, because then you can make that arbitrarily large. Yeah. So, yeah.
Okay, let's thank Jan one more time. Will you be